Hey Chem 100, it's Dr. Ricardo. This is the second video in chapter 14, and we're going to concentrate on acid-base titrations. So the first thing that you have to realize is that all acid-base titrations are neutralization reactions. And what a neutralization reaction is when you have an acid, usually in our case we're going to do a strong acid, something like HCl, aqueous, that if I allowed it to, it would completely decompose in water to give you hydronium ions and chloride. And a strong base, something like sodium hydroxide, that again, if I allowed it to hydrolyze in water, it would give you sodium ions and hydroxide ions. And when these two things react, neutralization reactions always, first of all, they go all the way to the right, so it's not an equilibrium. It's a one-way arrow, right? This reaction really wants to occur, right? So every bit of this is going to run out, every bit of this is going to run out of, whichever one is the limiting reagent will be the one that's left over, okay? And what do we make? Well, the H is going to get together with the OH to make 1 unit of water in this case. So it makes water. And the other product is a harmless salt, NaCl. So I wind up with water and a salt. So if I slowly added a known solution of HCl to an unknown solution of sodium hydroxide, in other words, what do I mean unknown? I don't know what its concentration is. As the HCl hits the sodium hydroxide, it'll neutralize it, making water and a salt. And that'll happen for a while until I add enough HCl until it reacts with the very last unit or the very last molecule of sodium hydroxide. And then once that's gone, all I'm doing is adding HCl to a saltwater solution because I've already used up the sodium hydroxide that's being titrated. So usually we put the substance that we don't know about in the beaker at the bottom of the titration, and we put the known standard solution, in this case HCl, up at the top. So I'll draw that for you, okay? But you could do it either way. It really doesn't matter, okay? But it kind of makes sense to put the one that you know about in the burette. So the burette is a long, skinny tube, and it has a valve at the bottom called a stopcock that you can open and close slowly. In the beginning of the titration, you're very far away from the end point, so you can allow the HCl to drip out of this pretty quickly, okay? And it's not actually dripping, it's actually flowing out of it. The interesting thing about the burette is it's got the 0 mark up at the top, and each time you go down, you can measure how much you add, right? So let's make this a 50 milliliter burette, so then when I get to the bottom here, I would have delivered, let me make this a little bigger, I would have delivered 50 milliliters of this solution, okay? So I start up here, and then what's down at the bottom? A beaker or an Erlenmeyer flask. I'll draw a beaker. And we put the sodium hydroxide down here, the thing that we want to measure. Now, if I'm starting with a solution here, I need to know its molarity and its volume. But if I'm just starting with a solid sodium hydroxide sample, I would just have the number of moles of it, and then I can just add a certain number of water. Remember, we're always titrating against the number of moles that are down here, not really the molarity and the volume, okay? It's really the number of moles. So you can start with a solid, add any amount of water to it, and be able to calculate how many moles of sodium hydroxide was originally down here. You're really concerned with the number of moles, okay? So in our case, this is going to be the substance that we know what its concentration and volume are. So I'll give you an example. A lot of times we make these 0.1 molar. And let's say I deliver it down to here. Add a little bit, add a little bit. Now what am I looking for? Well, what do I have down here? I have 0.1 molar. And then over here, I'm going to have an unknown concentration or an unknown number of moles of the other reactant, sodium hydroxide. So this guy's going to be known. I know its concentration is 0.1. This guy is unknown. I don't know how many moles are down here. Okay, again, if it was a solution, I can get its molarity because I have the number, I'll find out the number of moles, and then I'll just divide by the volume. So I'll make this that we would have added, let's say, put this into 20.0 milliliters of solution. So I can measure that. Okay. All right, so how am I going to tell once I've added enough hydrochloric acid to the sodium hydroxide so that they're in equal molar amounts? That's this special point called the end point. So the end, sorry, that's a D. So the end point is this special place when the solution is going to either change color or the pH meter is going to jump up, and we'll talk about that in a second. And at the end point, the key is the moles of acid added, right? You're adding them slowly. The moles of acid added is going to equal to the moles of base that are present in the bottom. Moles of base present, okay? So moles of acid added is equal to the moles of base at this endpoint. So, two ways to do this. The first way to do this is to add something called an indicator. How an indicator works is you add a little bit of it. The classic indicator for acid-base reactions is phenolphthalein. So phenolphthalein, you take a drop of this stuff and you put it into an acidic solution. If you, you put it into a basic solution. You put it into a basic solution, it's colorless, okay? It itself is an acid base at equilibrium. So when it changes forms from its acid form to its base form, it changes from colorless to this beautiful pink color, okay? So when you first open up the stopcock and add the HCl, what you're going to see is the pink might stay right at the very beginning because there's so much acid there, but it won't persist. As soon as you shake up this, or shake is not the right word, as soon as you swirl this beaker, that pink color will go away because the pink color can only persist if the HCl is in abundance, if you have more HCl than sodium hydroxide. So in the beginning, I've got a lot of sodium hydroxide, and I'm just slowly adding a little bit of HCl. It reacts, the HCl that reacts with the sodium hydroxide can't keep the solution pink. So it goes in, it turns pink for a second, but then all the HCl gets chewed up until I reach the point where I've added the same number of moles of HCl so that every single bit of the HCl reacts with the sodium hydroxide, and I don't have any of this left and any of this left, and all I have is this and this. At the end point, I get to this special place where I used up all of this and all of this. If I add them in equal amounts, they're going to totally react with each other, and the limiting reagent will be both of them. They're both going to go down to zero. That's why we add it slowly. I can't just dump some HCl in because I don't know how much to put in. So I have to put it in slowly. So I swirl it. The pink color stays for a second, then goes away. Swirl it. The pink color stays for 2 seconds and then goes away. Eventually, though, I get to the point where it doesn't go away. And that's how I know I should stop the titration. So here, I swirled it, and it's just a teeniest bit of pink, okay? Doesn't go away, and then I add one more drop, and it stays pink. Once it stays pink, I know I'm at the end point. I go back, and I read the burette. I see how many milliliters I have to add. So let's say I got down to here, and I used up all of this, right? So this amount that was up here from 0 up to this point, I'm going to make it 21.7 milliliters. I get to that line. If I started at 0 and I go down to 21.7, the 21.7 is how much that was added. So you add it from here. So the stuff that's missing, where did it go? It's down here. What's the total volume of this solution down here? Not that you're going to need it for anything, but you took the 21.7 and you poured it or dripped it into here. So you have 20, and then now you've just added 21.7 milliliters. Okay, and here's my solution at the end. It should be a total of 41.7 milliliters. Again, you're never going to need that number. You're going to need this if you want the concentration at the end. Okay, because we want to find out what was the original concentration of the base before I started. So that's the typical titration experiment, right? The second way that you can do it is rather than know when to stop by waiting for the color change, adding it slowly, you could take your beaker at the bottom and you could put a pH electrode into it. So here's my beaker at the bottom. Here's my original solution that I'm titrating. And over on the side here, I'm going to put a pH electrode in. And this will go over to a pH meter. And the pH meter reads what the pH of the solution is. Okay? So originally, you're going to start out with a very low value, something like maybe 2.50. Okay? Doesn't matter what it is. It's just a low value. Now, you still want to put your, this is the base down here. So originally, you're going to start out at a very high value. So let's make that 12.50 because it's the base. Okay, I still need my burette. I'm going to put my acid in here. And what I'm going to do is I'm going to open the stopcock, add a little bit of the known acid, read the pH meter, add a little bit more, read the pH meter, add a little bit more. What you'll start to see is a profile that looks like this. So what we want to do is be looking at how does the pH change versus the number of milliliters of acid added. Okay, you can also do this reverse. How does the pH change versus the milliliters of base that's added? So ours is starting up here. Before I add any milliliters of acid, it's going to be at 12.5, which is a huge number. Here's 7, here's 0 down here, here's 14. So there's our pH scale, right? So we're starting at, when I haven't added any milliliters of acid yet, I'm starting at 12.5, way up here. Now what's going to start to happen is, go back to the reaction. As I add the acid, it's going to drop the concentration. The acid is going to react with the base, and this stuff is going to slowly go away, right? As soon as this hits this stuff is always gone. So before I get to the end point, this is the limiting reagent. Okay, so the acid disappears. Why? Because it reacts with the base to make water and a salt. So basically what I'm doing is, open up the stopcock, allow some of the HCl in, it immediately reacts, I'm taking this away. So over time, the sodium hydroxide concentration is going to be dropping, right? Acid gets eaten up right away, but the sodium hydroxide, every time I add a little bit, it's going to keep on going down, down, down. This is a basic solution because it's got an excess of sodium hydroxide. So what you're going to start to see is first, pH will kind of go down nice, get a little quick bump. Okay, it'll go down nicely. But then it kind of gets buffered and it kind of goes down super, super slowly until you get close to the end point and then it drops like crazy. So this place where the pH changes super dramatically is your end point. So instead of looking for the color change, you're going to use the end point as the number of milliliters of acid to when you see this big change in pH. There'll always be one big change in pH when you do a strong acid with a strong base. So that's what you're looking for. If you do it the reverse and you put the acid at the bottom and the base at the top, okay, it doesn't matter which one is known or unknown, well, what you're going to get is something like this. Here's pH 7, here's 14, here's 0. this is the number of, let me make 0 down here, okay? This is the number of milliliters of base that's added. So now I've got the acid down at the bottom instead of the base, so the pH is going to start out low, maybe something like pH 2 or pH 3. And as I add milliliters of base first, the first couple of drops makes a little bit of a jump. And then it goes up very, very slowly till I get close to the end point. Then it rockets up and goes slowly again. So this place right here, if you drop a perpendicular line, this number of milliliters, right? Because remember, you were doing this a little bit at a time. You opened it up, you got to here. You opened it up, you got to here. You open it up. You can start to see when you get close, when the pH starts to change a lot. Okay? And this place right here would be the end point. The point where you added just enough acid to totally react with every bit of base that's in the solution. Okay? All right, so let's take a look at our first problem that we have to do. I'm going to do the first one in steps. It's a problem from the book. This is from page 457. Okay? They give you the balanced equation. Let's read the problem. I'm going to do it step by step, separate, and then I'll put them all together and do it in one long conversion conversion problem. Okay, so let's leave this up here. Okay, so here's the question. If 16.3 milliliters of a 0.185 molar solution of strontium hydroxide, notice this strontium hydroxide has 2 OHs per unit. Okay, so that's really important. The metal can deliver, the strontium can deliver 2 OHs. So that's why this is going to be 2 acids for each base as opposed to 1 to 1. So we're going to need to take into consideration this stoichiometric factor of 2 units of acid will react with each 1 unit of base because this guy has 2 for 1, right? 2 OHs. I make 2 waters and 1 strontium chloride. Again, I make water and a salt. These are the harmless things at the end. Okay? Which one's going to go at the top? I'm going to put the known 16.3 milliliters up in my burette. I know its concentration, and I know the number of moles that were added here because volume times molarity, especially volume in liters times molarity, will give you moles. So that's the first step that I'm going to do. I'll rewrite the balanced equation now, okay? Because this way I can move the textbook. So 2 HCl's plus SrOH2 aqueous, acid plus the base makes water, in this case 2 waters, and the salt. Okay. Salt doesn't contribute anything to the pH. It's hydroxide and hydrogen ions. Okay, well, what did we know about the strontium hydroxide? Let's write down everything we know about that. I'll read it to you. I have 16.3 milliliters. Okay, that's not going to cut it. We're going to need to switch that to liters. So how do I go to liters? I have to divide by 1,000. So move the decimal place 3 times. So go 1, 2, 3. How many liters is 16.3? 0.0163 liters, right? Because if we want moles, we want molarity times liters. And we do know its concentration. It's pretty concentrated, 0.185 molar. Okay, so that's what I know about the strontium hydroxide. Okay, what do I know about the HCl that's in the stomach acid, right? So the acid in your stomach is the strong acid HCl. Okay, well, they took some gastric juice. How much did they take? They took 25 milliliters of it and they gave it to you in liters. So you want to titrate the HCl and they gave you its volume, right? So how much of the gastric juice did you start with? 0.0250 liters. So this, I know its volume, but I don't know its concentration. 0.025 liters. Okay? And what do we want this guy? We want the molarity of this. Okay? Well, I can't just use MA VA is equal to MB VB here. right? The molarity of the acid is equal to the molarity of the base, the molarity of the acid times the liters of the acid is equal to the molarity of the base times the liter of the base, because this is a 2-to-1 reaction. So I have to take the stoichiometry into account. So what's the first thing I'm going to do? Let's get the moles of this. So the moles of strontium hydroxide, we know that moles is molarity of something times the liters. So the moles of strontium hydroxide is just these two numbers multiplied. 0.185 molar, right? That means moles per liter. Multiply by the number of liters, 163 liters, and you'll get moles. So that's just a straight multiplication after you change the 16.3 milliliters to liters. Okay? So 0.185 times I need an O in here. Stick an O in there, guys. Okay? Times 0.0163. Okay? That's 16.3, only expressed in liters, equals 3.015, so I'm going to call it 5, so I'm going to call that 3.02, right? That's close enough. 3.02 times 10 to the minus third moles. That's how many moles of strontium hydroxide I have. Okay, well, if I have moles of this, I can get to moles of this. Just look at the balanced equation and relate them. So here we go back to our stoichiometry that we've been doing all year. Or not all year, but at least the last month or so. This is moles of what substance? SrOH2 times, look at the coefficients of the balanced equation. For every 1 mole of SrOH2, there must have been 2 moles of HCl to reach the equivalence point, right? It's a 1 to 2 relationship. This will give me the number of moles of HCl. And then the last step is, if I want the concentration, I know the moles and the liters, I can just divide them. So the moles of SrOH2, the moles of SrOH2 is going to be just this number times 2. So that's going to be 6.04 times 10 to the minus 3 moles. And it's changed now to HCl. Okay, and what would the last step is? They wanted to know the concentration. Oops, sorry. This is the moles of HCl. Okay, right? So 3.02 times 10 to the minus 3 times 2 gives you 6.04. The molarity is then just equal to the moles of that substance divided by how many liters I started with. Okay, how much, this is the substance I'm dealing with. I now know how many moles there are. 6.04 times 10 to the minus 3 moles. And I need to divide that by the number of liters. How many liters of the gastric juice did they start with? 25 milliliters is 0.025 liters. Remember, it's got to be moles per liter. And this unit of moles per liter is molarity. Molarity is moles per liter. Okay, so do that division and you're done. That's the concentration of the gastric acid that you started with. 6.04 E minus 3 divided by, I didn't need parentheses, but it probably would have looked nicer if I put parentheses around that whole thing before I divided. Divided by 0.025. Okay. All right, so the concentration of the HCl in the gastric juice is 0.2416 molar. Okay, I have 4 significant digits here. The rest of the problem, it only seems to always have 3. Probably have 1 too many, right? So I should probably just call this 0.242. Okay, let's see how close I came to what the book got. Okay, they got 0.241. I had 6.04, they had 6.03, but that's certainly close enough. Okay, so now what I'm going to do is I'm going to set it up and go straight across doing it just by the factor label method instead of using formulas. Okay. So if I do it that way, let me keep this at the top and I'll go across this way. Okay, so what's my starting point? Well, I need to start with an amount, not a concentration. A concentration really is a conversion factor. So the amount that I'm going to start with is the substance that I know everything about. I want to see how much HCl I need to reach the equivalence point, right? But I know how much of this I use to get there, right? So that's what I'm going to start with. So I'm going to start with 16.3 milliliters. You know what? Let me just do one thing. Let me start way, way over on the left because it seems like I'm going to have to use a lot of paper. Okay. So, 16.3 milliliters of SrOH2 is my starting point. Okay, can't work in milliliters, have to go to liters. There are 1,000 milliliters in every 1 liter of anything, including strontium hydroxide. Now, at this step, I'll have liters of strontium hydroxide. Okay, need another brackets. Now, this is kind of cool. I'm in liters of strontium hydroxide. How do I get to moles? Well, the way I get to moles is I'm going to use this as a conversion factor. What does this mean? Well, this means that there, in every 1 liter of solution, there are 0.185 moles of strontium hydroxide. So here, this is using molarity as a conversion factor. And what substance are we talking about? Still Sr2OH. Okay, so here, using molarity as a conversion factor. Goodbye liters, goodbye milliliters. Hello moles. Okay, now I have moles of strontium hydroxide. How do I get to moles of HCl? Use the coefficient of the balanced equation. Okay, this is probably easier, right? For every 1 mole of strontium hydroxide that went in, there must have been 2 moles of HCl. Okay, this is going to give me moles of HCl. Okay, that's as far as I can go in terms of using the conversion factor. The last step to get the concentration, I'm going to use the formula, right? Because this is going to give me the moles of HCl just like it did before, and then I just need to divide it by its volume. I don't really know of a good way of adding that last step. I think it's probably easier to see it from a formula. This one, though, you have the amount in the volume of the solution, change it to liters, and then use molarity as a conversion factor. Okay? That's this step. And this step is nothing new. This comes right from the balanced equation. Okay, so let's get off here. Okay, I could probably just take this and then just multiply it by 1 over, but I don't like to do that. Okay, so let's get the moles and then we'll do the last step using the formula. So 16.3 divided by 1,000. Okay, we saw that number before. Times 0.185. Saw that number before. Times 2. And we saw that number. So I got what they got this time, 6.03 times 10 to the minus 3 moles of HCl. And the last step, really, you just need to take this number and divide it by the volume. The molarity of the HCl, the molarity of anything, is its moles divided by the number of liters of the solution. Okay? Which number of liters? The original amount. The original amount was given to you in the question, I'll show that to you in a second, as 0.025 liters. Gotta have liters. You can't put milliliters in here, but they actually did give it to you in liters. Okay, this will give you moles per liter, which is molarity. Okay, we did that before, so we know what the answer is going to be. I'm going to get 0.241 molar HCl, and that's the answer. So I'll put this on the paper for you to see if you want to make a copy or take a picture. Okay, this is doing it straight across in one step, and then do this the last step. They show you the way they did it. I think they kind of did it the same way, right? At the end, they got moles, and then they divided by the number of liters. This was given to you. It's the original solution of the gastric acid that you started with, right here, right? I don't know why. They were nice. They gave it to you in liters. Usually somebody would express a small number like that in milliliters, right? That's 25 milliliters. Okay, let's do just one more question. What I'm going to do with this one is I'm going to take an unknown solid and we'll do a titration reaction on it, okay? So in this case, let's say I have an unknown acid, right? HX. And I know it's a monoprotic acid. It just has one hydrogen to deliver, okay? But I don't know what the other part of this, maybe this is nitrate, maybe this is chloride. I don't know what it is, okay? So I have an unknown acid, okay? And it's in a solid form, okay? So I have a certain amount of it. So let's say I have exactly 0.1 grams of this unknown acid, okay? So what I'm going to do is I want to find out how many moles are in that sample, because this way I can, an unknown acid, unknown, and let's say this guy is a solid, right? I didn't dissolve it in water yet. So I'll start that again. I'll write it a little neater. Okay, so we said we had exactly 0.1 grams of this new unknown acid, HX. And if it's solid, it's pure, right? In the solid form. Not dissolved yet. So it's pure. All right, so what am I going to do? I'm going to take that acid and I'm going to put it all down in the bottom of my beaker. Okay? So there it is. Because remember, when you're doing the titration, you're titrating against the number of moles. So we'll be able to find out how many moles of the acid is there, and then we can find out the molecular weight of the acid and other things like that. Let's put some water on top because I need to dissolve it. Doesn't matter how much water you have, because by adding a lot of water or a little water, the water isn't going to react with the base. It's going to be the acid. So all that the water is going to do is you just need to put enough in so that it dissolves. And now it's dissolved. They're all not sitting at the bottom. It's totally dissolved. Okay? So all the HX dissolved into solution. Okay? All right. So the next thing we need to do is, well, let's write the neutralization reaction. The neutralization reaction is once the HX is dissolved, it's going to react with my base, and I'm going to purposefully use base that I always use, which is sodium hydroxide. But it doesn't matter. It could be potassium hydroxide, lithium hydroxide, anything. Okay, and I'm going to know how concentrated my solution is that I'm going to use. Well, this is a neutralization reaction. Neutralization is the reaction of the acid with the base to make water. You can see the water there. Look, OH and H. And the salt. What salt do I get? HX. Excuse me, NaX. Okay. All right, so there's my acid. I put a little bit of my indicator in. So my phenolphthalein in acid solution is pink. In base solution, it's colorless. Okay, so I don't have pink. Well, actually I use red. So I'm going to start out. And this time it's going to start out colored. Okay. Take a burette. Fill it up with a known solution. Here's the zero line. What am I going to put in here? A known solution of sodium hydroxide. Let's say we have 0.2 molar sodium hydroxide. Okay, open up the stopcock. Let some in, swirl it. If the pink color persists, keep adding. Keep adding, keep adding, keep adding until the solution, this particular indicator, the solution becomes colorless. If it's colorless, it goes from pink. The moment it turns colorless, stop adding it. Okay. Let's say it took 31.2 milliliters of the 0.2 molar sodium hydroxide. Okay, that's how much I used up. This is now down there. The moment it turns colorless, that's the end point. What's special about the end point? The end point is the place where the moles of acid are equal to the moles of base. Right? I've added just enough sodium hydroxide to neutralize all the HX that's at the bottom, and at that special point, the moment it turns pink, I don't have any of this, and I don't have any of this. All I have is this and this. If I add even one more drop of sodium hydroxide, this solution is going to turn basic. And that's why it's going to turn pink, right? At pH 7, it probably might still be that's why it's going to turn colorless. So if I was looking at this on the graph, this one, since the acid's down at the bottom, this one would look like this, right? And this end point here would be 31.2. So I could do this either with adding an indicator that changes color, or having a pH meter and watching the pH meter change, right? This is 0, here's 7, here's 14. So I measure the pH versus the number of milliliters of base that's added. So this is 31.2 milliliters of base added. Okay, so I have the molarity and the concentration of something. Anytime I have molarity and concentration, what can I do? I can multiply them to get moles. So the moles of NaOH used is going to be the liters. This has got to get changed to liters. What is 31.2? If I express it in liters, 0.0312 liters times 0.20 molar. Okay. So the moles of sodium hydroxide are equal to those two numbers multiplied. 6.24 times 10 to the minus 3 moles. Okay, so now I know how many moles was originally in this solution, right? And I independently know its mass. Well, I'm going to put those two facts together to get the molecular weight of the substance, and that'll help us identify what it might be. So this is a great technique to determine the molecular weight of a pure unknown acid. Okay, so how many moles is it? There are 6.24 times 10 to the minus 3 moles of the stuff. Okay. Now, very important, let's look at the stoichiometry. Since this is one-to-one stoichiometry, I should have done this first. 1 mole of NaOH. Oh, let me start with this, sorry. Let me start with the NaOH, right? So 6.24 times 10 to the minus 3 moles of NaOH. Look at the balanced equation and see what the stoichiometry is. For every 1 mole of NaOH that goes in, 1 mole of HCl must be present. This is one-to-one stoichiometry. Okay? So, a number multiplied by 1 divided by 1 gives you the same exact number. All I'm doing is changing the units. And that makes sense because at the end point, the moles of acid are equal to the moles of base. And in this case, because it was one-to-one stoichiometry. Okay, last step. Make it a little bit bigger. The molarity of, the molar mass of something, right, is the number of grams per mole, right? Think about that. Well, we independently have the moles that we just solved for, and we had the grams all along because we started with 0.1 grams. So, if you are working on an unknown and you want to know its molar mass, weigh out a certain amount of sample, do the titration, independently determine the moles in the denominator, and then just take the grams that you used divided by the moles. So this guy was 0.10 grams. So that's the last step. The molar mass of anything is the mass of the sample divided by the moles of the sample, where you got this from the titration. Okay, so let's see what we got. We have 0.10 grams for the numerator and 6.24 times 10 to the minus 3rd moles. Grams per mole is molar mass. Right? It's how many grams it takes to make a mole. We know the mass of the sample that we started with, and we figured out from a volumetric titration how many moles it has. Never went to the periodic table because we don't know what the stuff is yet. Okay, maybe we can guess at it at the end. Let's see. So 0.1 divided by 6.24 E minus 3. I got the molar mass of this guy is 16.0. A little small. It would have to be a very, very small acid. Okay, very light acid. Okay. We know it has one H on it. Let's take a look at the periodic table to see if we can make a guess. Now, I just made up this problem, so it's not gonna work out proper. Okay, but if I have something like, an H and an N, right? It was nitrogen is 14, or something that was 15. I need something that's 15 and one more for the H that's on there, okay? But for you, you stop right there, okay? You can't guess at what it is in this case because it didn't work out perfectly, okay? All right. If I give you this on the quiz, though, I'll make sure that it works out to something that you get a whole number. Okay, so that's it for this lecture. Again, in cases like this, where you are asked about the concentration of the solution, you can use a simplified version because this is one-to-one stoichiometry. This is always true. Not only are the moles of acid equal to the moles of base, but moles of acid are equal to the molarity of the acid times the liters of the acid, which is equal to the molarity of the base times the liters of the base. This reminds you of the dilution formula. It just happens to take the same form as the dilution formula, but what we did with the dilution formula was we were able to substitute V's in here so you could work directly with milliliters if you wanted to. You can do that here too because you're being consistent. So since you use, as long as you use the same volume unit here and here, you can say that for a titration, the molarity times the volume of the acid is equal to the molarity times the volume of the base. Okay, and there's only one more stipulation about this. This has got to be 1-to-1 relationship between the acid and the base, right? Like the one that we had here. One of these for one of those. Then you can use this super simplified formula. Okay? You're never wrong though, just titrating and determining what molarity times liters are and getting the moles of the substance and then dividing it by liters. Okay? So in one-to-one cases, you get this very simple formula. The example we did before that, we would have had to be careful. We would have needed to put a factor of 2 in, because if you remember in that case, our neutralization wasn't 1-to-1. It was a 2-to-1 reaction. Okay, so you can't really just use that super simple formula because you need to take care of this factor of 2. Okay, so that's it for our titration video. We'll see you next time.